Okay, so for the last section, we're going to talk about regression. So up to now, we've discussed Pearson's correlation and how that really defines the relationship between two variables in a linear way. When graphing Pearson's correlations throughout the lecture and within the book, you'll see that we are typically introducing a line to really capture these relationships. And these lines are very useful because it provides us an opportunity to easily show the relationship between the two variables. It also serves as a measure of central tendency for the relationship between each of our variables and can be used for a prediction. And when we are adding this line to our correlation statistics, that is exactly what we're doing with regression. That is a regression analysis to define the line that captures the relationship between each of our variables that are correlated. And so this is an example of us graphing the correlation between SAT scores and grade point averages. And so each of these individual dots represents the correlation. And then what we have here is the line that really captures the overall tendency between these two variables. So this is our regression line right here. So for the regression line, what does that look like? Well, the general equation is y equals b times x plus a. X and y are our variables. A and b are fixed constants. A represents the intercept, and so this is the value of y when x is 0, and b represents the slope. So how much y changes for every 1 unit change in x. And so when making a regression equation, what we want to do is find the best fitting line. So there's a lot of ways to define the best fitting line, but the way to really think about it is what line minimizes our error the most. And so we can use mathematical formulas to find out what minimizes the errors the most and what line would be most representative of the actual data. And so if we are coming up with a regression equation that has a lot of error in it, it's not going to represent our data as well as something that minimizes on the error and really captures the data. And so what we're interested in is the distance between that predicted value of y and the observed value of y. And this distance, this gives us the error. So we can see here that some of the error terms are going to be negative, some are going to be positive. And so what we want to do is we want to square all of the error terms to get them all to be positive, so they're not canceling each other out. And then we're going to add those up. That will give us an indicator of how much error is captured within different regression equations that we could develop. So this slide really captures a lot of what I just went over, that y hat is the predicted value of y, and that the distance between the observed y and the predicted y represents the error term. What we do is we square those terms so that they are all positive, and then we're going to add them up. This is called the least squared error solution. This method gives us an idea of which regression equation is most appropriate for our data and includes the least amount of error. So the real question becomes, how do we find this best fitting line? Well, what we're really looking for is to define this regression line equation, which we talked about earlier. So this is y hat, the predicted value of y for a given slope times a specific x plus the intercept. And so what we're looking for is a regression line that will give us a predicted value of y for a particular x that minimizes the amount of error in the regression equation. And so what we want to find is an appropriate slope and intercept that does this. So how can we calculate the slope? Well, there's two formulas that we can use. For the slope, we can use SP over the sum of squares for x, or the regression coefficient for x and y times the standard deviation for y over the standard deviation for x. As far as the intercept, one of the key characteristics about a regression line that minimizes the amount of error is that they will pass through the mean of x, mean of y point. And I think that's clearly shown in your book on page 455. And so you can use that as a starting point to find out what is the most appropriate intercept. And so we can take the mean of y times our slope, minus our slope times the mean of x to figure out what would be the most appropriate intercept. And by using these formulas, we can then calculate and find what our regression equation should be that minimizes the amount of error. So from that, we can use that equation to make predictions. And so what we can do if we have particular specified values of x, we can put them into this equation and find out what their predicted value of y is. But using regression equations for prediction, it's not going to be perfect. So you're always going to have some error, some element of imprecision. And this imprecision is captured by the standard error of the estimate. And so with almost everything that we've discussed, we've had some type of estimate to find the error that might be there. So whether it be variance or standard deviation or standardized error, and now the standard error of the estimate for regression. And so for regression, what this really looks like is the sum of squares for the residual or the error over degrees of freedom. And so we can see here that what we're doing is we are calculating the deviation from the observed y to the predicted y. We're squaring that to make them all positive so nothing is canceling each other out, and we're summing that. That's exactly how we calculate error. We're dividing that by the degrees of freedom, and so we have two variables that we are most interested in a simple linear equation. And so our degrees of freedom are going to be our total number of participants minus 2. This should be very familiar to you because for degrees of freedom for a Pearson's correlation, this is exactly how we calculated it. We take the square root of that to get a standard measure. So this becomes the standard error of the estimate. So these graphs just give us a very clear example of a perfectly fit regression line versus an imperfectly fit regression line. And what we can see here for the first regression line is that each of the points, each of the data points for x at a particular value and its corresponding observed y value is perfectly matched to the actual line. And so we don't see any error here. However, with our imperfectly matched graph, what we can see, or line rather, what we can see is that we're going to have error throughout. And so what's really important to notice about these two graphs is that they have the same exact regression equation. And so knowing the regression line equation doesn't provide you information about the accuracy or the error that is captured in that equation. What you need to know is the standard error of estimate. The standard error of estimate, as I mentioned, provides us information about the standard distance between the predicted y values on the regression line and the actual y values. And so whenever we're evaluating the accuracy or the precision of a particular regression line, that's what we need to consider, not just simply the equation. And so one of the things to think about is, and I think is captured very well in these two graphs, is what's the relationship between the standard error estimate and our correlation coefficient. And so as R increases to perfect, whether it be 1 or -1, the standard error estimate is going to decrease. Why is this? So essentially, as R increases, all of our data points are going to become closer together, and therefore we can fit a line that's more tightly fit to that data. And for that reason, it's going to be more precise, more accurate. Our standard error is going to be lower. So there's a few things that we need to know when we are predicting regression equations and just overall variability in our different scores. So one of them is the sum of scores for the regression, and that's actually very easy to compute. And if you think about it conceptually, what are we doing here with when we're looking at the predicted variability in y-scores? Well, if you think about r squared and what that means, the coefficient of determination, that is the amount of variability in one variable that is accounted for, attributable to, shared with the variability in another variable. And so that essentially gives us an idea of how these two variables are relating to one another and the proportion of variability that is shared. And so if we take that value and then multiply it by the sum of squares for the y variable, that is going to give us our sum of squares for the regression. So it inherently considers how x and y relate to one another, and then imposes a further conceptual piece, which is going to be the sum of squares for y. Now, that's going to be the predicted variability. When thinking about regression equations, so we do have our predicted variability, but we also have our unpredicted variability. So what is that? That's going to be just 1, because if we add up all the total variability, it's going to equal 1. 1 minus that coefficient of determination times our sum of squares for our y variable. And so this represents the sum of squares of the residuals. And so what's not accounted for by that regression equation? What is left over after we have fit the data as best we can with a line that minimizes the error? And so there's another way of calculating the standard error of estimate based on R, and we have that right here. And so basically we would just use the equation for the sum of squares for the residual. So what's not accounted for by the equation divided by the degrees of freedom n minus 2, take the square root of that. And so you can use either this equation right here or this one up here. This one tends to be a bit more tedious, but you have to know the background to get to this one. The last thing to go over with regression is hypothesis testing. Hypothesis testing for regression is very similar to ANOVA. Regression hypothesis testing uses the F ratio to evaluate two mean square values. And remember that mean square is a sum of squares divided by a degree of freedom. And the null hypothesis with regression is that the slope of the regression line, so the b or the beta, which is a standardized slope, is 0. And so what this essentially says is that with our slope, there is no variability in y that is being accounted for by x. And so our alternative hypothesis is that the slope is statistically and significantly different from 0. And so how do we calculate the mean square and the F ratio for a regression? Well, we're going to eventually have to get down to this equation right here, which is the mean square of the regression over the mean square of the residual. So the mean square of the amount of variance that is accounted for by the equation over what is not accounted for by the equation. And so for the mean square of the regression, what we're going to use is the sum of squares of the regression divided by the degrees of freedom for regression. We can go back here to sum of squares for regression. So this is again going to be our correlation coefficient just multiplied by the sum of squares of y. The degrees of freedom for the MS for regression is actually just 1. And so what you find is that this value up here is just going to be equal to the sum of squares for the regression. For our denominator, we're going to have the sum of squares of the residual over degrees of freedom for the residual. Now, for this residual, it's actually going to be n minus 2. And so the reason for that is because we do have our two variables, and we are needing to allow for all the points within each of those variables to vary freely except for one. And so for the MS for residual degrees of freedom, we have to remember that that's going to be n minus 2. Up here, degrees of freedom is always going to be 1 because we're interested in one regression slope parameter. And so coming down here, we put this information together, we find our F ratio test statistic, and then we evaluate it according to our table with the degrees of freedom equal to 1 for the numerator and n minus 2 for the denominator. And so here is just the partitioning of the sum of squares and degrees of freedom for a regression analysis. So what we're trying to do is account for variability in y, and so we have separated that into the variability in y that is accounted for by the regression equation, and then the variability in y that is not accounted for by the regression equation. We've also separated out our degrees of freedom into our degrees of freedom for the regression of 1, and then degrees of freedom for the residual of n minus 2. And so that's all that you should need to know to answer questions on the exam review. If anything is unclear or if you have any questions, you can always reach out to me. You can also use your book as a resource. I would strongly encourage you to. Regression will not be on the final exam, but this information is very important and you should have some familiarity and some introduction to it.